mathematics the prize, and they merged with us to establish this prize in honor of Ramanujan, who was a role model for mathematicians, especially from developing countries, given the conditions that he had to become a mathematician and do important research. So I will read the statement of the prize. So in 2005, ICTP established the Universal Ramanujan Prize for young mathematicians from developing countries, named after a mathematics genius from India. This prize is awarded annually to a mathematician under 45. Since the mandate of ICTP is to strengthen science in developing countries, the Ramanujan Prize has been created for mathematicians from developing countries. Since Ramanujan is the quintessential symbol of the best in mathematics from the developing world, naming the prize after him seemed entirely appropriate. The Ramanujan Prize is funded by the Norwegian Academy of Science and Letters through the Able Board, with the cooperation of the International Mathematical Union. The Able Board is named in honor of the great Norwegian mathematician Niels Henrik Able, and it is enchanting that the names of these two extraordinary mathematicians should be linked to this prize. And in particular, this year, the prize winner is very talented mathematician. We are very pleased to have him here. So I will read the citation. This is for 2012 Ramanujan Prize citation. This year's Ramanujan Prize is awarded to Professor Fernando Codá Marques from the Instituto Nacional de Matemáticas Puras e Aplicadas in Rio de Janeiro, Brazil. It's IMPA. The prize is a recognition of his several outstanding contributions to differential geometry. Together with his co-authors, Fernando Codá Marques has solved long-standing open problems and obtained important results, including results on the Yamadi problem, the complete solution of the Jones conjecture, counterexamples to the rigidity conjecture of mean U, connectivity of the space of positive curvature metrics on an orientable trimanifold, and most recently, a proof of the Wilmore conjecture. The prize is supported financially by the Norwegian Academy of Science and Letters to the Able Board with the cooperation of the International Mathematical Union. So now you see the program. So after these few words from myself, then we will have, after that is a message from Ingrid Dobesis from IMU, the International Mathematical Union. She will be on video. After that, Professor Claudio Rezo will be given some remarks regarding the importance of mathematics to the work of Fernando Codá Marques. And he will be followed by the presentation of the award, a few words by Helge Holden, who's also here with us from the Able Board. And after that, then Fernando Codá Marques, who is the Ramanujan Prize, he will use the Ramanujan Prize lecture at the end of the ceremony. So, okay, so let's try to have Ingrid.
Hello, I'm Ingrid Dobesis. I'm the president of the International Mathematical Union. I'm very sorry that I can't be here today with you to celebrate in this wonderful event the celebration of this year's Ramanujan Prize winner. The IMU attaches enormous importance to this prize, a prize for mathematical contribution from a young mathematician from a developing country. And it's only at the very last moment that we realized that the IMU representative couldn't make it to this year's celebration. So please forgive us that we are not here in person. I do want to extend my congratulations to this year's prize winner, Fernando Codá Marques, for his contributions in differential geometry. I also want to extend my thanks to the Institute in Trieste for its ongoing support of this prize and for hosting the award ceremony this year, and to all the members of the jury who contributed through their work to the selection of this prize winner. So congratulations again. Please have a wonderful celebration, and we're with you in our thoughts. Thank you.
table to convert that.
That's my contribution, but that's not why I was doing it. Well, today I have a beautifully impossible mission. I have 10 minutes to describe to you the work of this year winner. Okay. So I actually start from the very beginning. I assume that there were many people not really familiar with geometric analysis and differential geometry in the audience, so let me, oh, sorry, I forgot. First, who is the winner? In 3 words, in 3 sentences, he is horribly young. He got his PhD at Cornell in 2003, and just to, as a highlight of his recognition inside the mathematical community, he's already been a speaker, invited speaker at the International Congress of Mathematicians in 2010, which is kind of one of the highest honors the mathematical community gives. And as another highlight, I mean, of course, this means almost nothing, but if you just see, I can tell you, there could be another slides like this, okay? Of another 6 publications of this level and this good. Now, in order to describe a little bit his work, actually, you see the first line here is kind of special in this list. And very recently, in February, Fernando and André Neves of the Imperial College announced the proof of a long-standing conjecture in differential geometry and geometric analysis called the Wilmore conjecture. So that's kind of a singularity in his work, and that's what he's going to talk about in his lecture. Okay, so I would like to give you quickly an idea of everything else, or at least a couple of the things which are below the Wilmore conjecture. Okay. Now, what does a differential geometer with some taste in analysis? I mean, somehow the fundamental problem is, given a space, a manifold, compact or non-compact, one looks for the best metric you can put on this manifold. This is it's a problem which starts 200 years ago in some sense, and somehow we have a maybe non-trivial case in our minds. Basically what happens in dimension 2. Dimension 2 tells us that on any compact Riemann surface, so we can prove, actually this was proved by many people, depends which country you come from, you give a different name to the guy who proved it, so I better shut up. I mean, there is an Italian, a French, a German, especially in this moment, it's better to be in the present European situation. Okay, so it's a classical theorem at the beginning of non-Euclidean geometry, let's say. So any compact Riemann surface, there is a unique metric of constant Gauss curvature. Now, actually, if to define curvature is already a problem in differential geometry. And actually, there are very different notions of curvature, but in dimension 2 they all coincide. Okay, so whatever notion you pick, this theorem is going to tell you exactly the same thing. While if you go to higher dimensions, different notions have different flavors. Of course, one could ask to have the full Riemann tensor. So if you really want to encode all the geometry, I mean the Riemannian geometry in one object is the Riemann tensor which dominates everything. And you can ask to find a metric whose Riemann tensor is completely constant. Constant means covariantly constant, of course. On a manifold it doesn't make sense, it's a tensor. So now, but very few spaces have such thing. Okay, this was the first theorem, it's called the fundamental theorem in Riemannian geometry, so proved by Riemann. So if the sectional curvature is constant, then the manifold is actually very simple. It's either it's a model space, it's Euclidean, it's a sphere, or it's a hyperbolic space modulo a subgroup of isometries. Okay? Now sectional curvature, it's, I mean, this assumption is almost, I mean, it's the same thing as the whole curvature. But so what do we do? So very few spaces have constant curvature in the full sense. So we extract a weaker information, which is called the Ricci curvature. Basically, we contract 2 entries of the Riemann tensor, and we define the Ricci curvature. And then we can ask, which spaces do have a metric of constant Ricci curvature? Constant, again, covariant constant. translates exactly in the Einstein equation, the Riemannian Einstein equation. Okay, so basically the question becomes which spaces are Einstein? The Einstein's equations look like this, where C is a constant. Okay? So the metric must be proportional to the Ricci curvature. The Ricci curvature should be proportional to the metric. Okay, why are we doing that? Well, if we know that the space has an Einstein metric, of course we know quite a lot about it. For example, in the complete case, if the Ricci curvature is bounded away from zero, we know that the manifold is compact. This is actually very interesting for me. These are classical theorems. Okay, proved around the 40s, the 50s, 1949. Okay, a compact manifold of positive Ricci curvature is simply connected. That's another. I'm just highlighting some kind of consequences of the fact that you know that the space is Einstein. And then, of course, this is the only theorem of this century. I mean, it's the Perelman-Hamilton solution of the Poincaré projection, for example. So a compact simply connected manifold has an Einstein metric of positive curvature. Hence, by the previous theorem I mentioned about Riemann, it's a sphere. Okay. So this is the kind of the prototype consequences you would like. So what are the difficulties? I don't have time, absolutely no time to tell you why it's a very difficult problem to describe and to decide which spaces are Einstein and which are not. But just as a highlight, let me tell you one difficulty. This is due to Lebrun, for example. There exists homeomorphic, but not diffeomorphic manifolds. One is Einstein and one is not. Okay, so the problem of having an Einstein metric does depend on the differentiable structure, not just on the topological structure. And we don't really have many tools to study differentiable structure. But the Ricci tensor is still a tensor, still quite complicated, and we know actually that many spaces do not have an Einstein metric. So what else can we do? We can contract even further. So from a tensor, we contract the last two indices, and we get a single function, what we call the curvature function, the scalar curvature function. It's called S. So which spaces have a constant scalar curvature metric? Well, this was a classical theorem. I mean, it started in the 60s, and then the final proof arrived in 1984 by Rick Shane. So in fact, every manifold has a metric of constant scalar curvature. So in fact, having a metric of constant scalar curvature seems a very weak condition, in fact, an empty condition. So what is interesting around here? Well, which sign is it? I mean, positive curvature, zero curvature, negative curvature. The sign of the scalar curvature that you get, it's an interesting invariant. This turns out to be an extremely delicate, oops, okay, mistake. So let me show everything. And there is a peculiar phenomenon proved by Katzmann and Warner, that if you manage to produce a metric with curvature 2 on a manifold, you are certainly able to produce a metric of curvature 1, 1/2, 0, -1, -2. So, if you, whatever, in some sense, the interesting thing looks like what is the highest curvature you can get on a manifold. From there downwards, you can do whatever you want. In particular, it's extremely interesting to ask whether a manifold has a metric of positive scalar curvature. Okay. This actually looks a bit surprising the first time you see it. For example, a three-sphere has a metric of positive curvature, the round one. It also has a metric of zero curvature, and this also has a metric of -1 curvature. Okay. This is kind of not completely into it. Now, so how do we try to tackle the problem? From a variational point of view, that's what Fernando means. I'm starting getting closer now to Fernando's work. So, critical points of the Einstein interaction are Einstein metrics. And if I look for constant scalar curvature metrics, I restrict this functional to the space of metrics which are obtained from one metric, which I call G0 there, and I multiply by a positive function. This is just u to the power 4 over n minus 2, just for convenience, just to make look a bit better the formula, but that's just a positive function. These are called conformal changes. Geometrically, it means you are not changing the angles among directions. So, okay, we know, I mentioned the general theorem before, Aubin and Yao show that this functional always has a critical point, but the fundamental question is how many critical points does it have? Is it possible to build a reasonable Morse theory for this function? This function does not satisfy any Palais-Mail type condition. Okay, so it's quite bad from the analytic point of view. So that's where. So Shane himself posed a conjecture, which is called compactness conjecture. So if a manifold is non-conformally equivalent to the standard sphere, which is kind of a special case in all this story, because there's a classical theorem by Obata saying that if the conformal group is non-compact, then the manifold is the sphere. It's the only case, because of the only exception. Okay, but if this is not the case, then he conjectured that the set of critical points, so the set of metrics of constant scalar curvature C, should be compact in the C2 topology. Of course, you cannot expect uniqueness, but at least compactness. Okay? That would be a nice starting point for a Morse theory, which the Max-Tillerman at least. And he observed that at least in low dimension, this conjecture actually follows from the positive mass theorem. And then actually, and this is a good moment to connect to the work of another Ramanujan Prize winner, Professor Shi, who celebrated it 2 years ago. For example, he and Tan extended this approach to up to dimension 11 or up to dimension 7 and for spin manifold dimension 11. You see that these dimension bounds or spin conditions are put just to be able to use the positive mass theorem. I don't that now. So here comes the first theorem by Fernando I would like to mention. First theorem, Curie, Marques, and Shane proved that the compactness conjecture is true without any assumption on spin or something like this up to dimension 24. Now 24 sounds like a completely weird number in this story. It's not. So you might wonder, is this just a technical number coming inside some tricky part of the proof? So then they answered the question. So Simon Brendel first, and then in a joint paper, Brendel and Marques completely closed the story. So it's the conjecture is false from 25 onwards. Why 24 now? So now we know that 24 is not an accident of the proof, I believe, but Fernando is here. I cannot justify the number 24 by any geometrical meaningful. Second, another 2 minutes and I'm done, because what else Fernando did? For example, this is actually a piece of work that I find really good. So, I justified before the question to look for which manifolds have a metric of positive scalar curvature. This is an interesting problem. But actually, there is once you know that there is a metric of positive scalar curvature, obvious questions. How does it look, the space of metrics of positive scalar curvature on a given manifold? This connects to very classical theorems. For example, on the 2-sphere, which of course has a metric of positive scalar curvature, the round one, there is any 2 metrics of positive curvature are path connected. You can always join them by a continuous path of metrics of positive curvature. This is actually an application of the uniformization theorem. It actually can be proved also by Ricci flow in modern methods. So, question: what happens in higher dimension? Is the space of positive scalar curvature metrics connected or not, or path connected? Well, we knew almost 40 years ago that this cannot be true in general. In fact, even for spheres. So, Hitchin found by applying the index theorem for the Dirac operators here. So, spheres of dimension 8k and 8k plus 1, when k is positive, have spaces of positive scalar curvature which are disconnected. This is just the beginning of the story. Of course, many people try to describe other situations. Okay? So, let's ask the question not just on the sphere, but on any manifold. Well, first observation, we know how the manifold looks like thanks to Peregrine. Okay, so the manifold is not completely mysterious. It has to be the sphere portioned by a group, a spherical form, connected some with finitely many copies of S2 process 1. This is kind of an output of Perelman's proof of the Poincaré projection. So, okay, one kind of basic, I would say, theorem of Marques is to prove that in 3 dimensions, the space of metrics of positive scalar curvature, I would say the modular space, because really what we really proved is this space modulo the diffeomorphic group. Okay, can chucks on the space of matrix by moving. This is path format. So you can see the simplicity of the statement, I think, explains. And actually, we didn't know this even for the three sphere. Yeah, so it's not just. And since we are an institute in theoretical physics, let me mention that this type of approach, that the approach we developed to this kind of problem, has some interesting application to general relativity. So, for example, actually the same argument, of the proof of the positive scalar curvature theorem proves that the set of asymptotically flat metrics of R3 of order 1 means they actually came to the Euclidean metric at infinity at least of order 1. Okay? That's what I mean by order. And of zero scalar curvature is path format. Okay? This is of course a clearly an interesting set of metrics if you do general relativity. Okay? And another theorem with this flavor, if you take the set of trace-free asymptotically flat solution of the vacuum-Einstein constraint equation, so you complicate a little bit the story, of order 1, 2. Here the variables are a metric and the second fundamental form of the space-like tree space. Okay, so it's a metric and the second and another tensor. So you would like 1 to decay to the flat metric of order 1 and the second fundamental form of the k to 0 of order 2. That's what I mean by 1. This is again path format. So he closed this section of his work by asking if this theorem holds for the full set of solutions of the vacuum-Einstein equation, constraint equation. The problem is that they do not induce, in a suitable sense, metrics of positive curvature. So these methods, at the moment, doesn't. Okay, so as you can see, I stop here, and this is just highlights of really beautiful work that Fernando did in the last few years. So I personally congratulate him, and I let Professor Holden to take mine.
Thank you very much. So now to follow with the program, we will have some words from Professor Holden from the Able Board, and before the presentation of the work itself. Please,
Ladies and gentlemen, it's a pleasure for me as the chair of the Able Board to participate in this Ramanujan Prize ceremony. First, I would like to thank the ICTP for hosting this event, which is a great event for the prize. When the Norwegian government in the fall of 2002 decided to create an Nobel Prize, the Prime Minister gave two arguments. The first and foremost reason was to establish an annual prize to recognize mathematical accomplishments on the highest level internationally. The second argument was to use the prize to stimulate the interest in mathematics among the young. Norway had experienced, like many other nations around the world, a decrease in the interest in mathematics and natural sciences among children, pupils and students, resulting, for instance, in the national shortage of engineers and teachers in schools. The lack of mathematical competence is, of course, not restricted to developed countries. As part of the second responsibility, the Able Board decided to allocate funds to the International Mathematical Union, IMU, to support mathematicians in developing countries with an annual amount of 50,000 euros. As part of these funds, it was decided to award an annual prize for outstanding young mathematicians, and in this context, young is less than 45 years, and you see that this year we had no problems with the age limit, from a developing country. The prize is administered by the ICTP here in Trieste, and the prize committee comprised of mathematicians appointed by the IMU, the ICTP, and the Able Board. Very appropriately, The prize was named after the Indian genius Ramanujan. Ramanujan and others share many similarities in their lives. They were, to a large extent, autodidacts. They received rudimentary education and had the fortune that their talents were discovered. Ramanujan by the English mathematician G.H. Hardy, and Abel by his high school teacher, Holmo. And tragically, they also shared the fact that they both died young. Abel at the age of 26 and Ramanujan at the age of 32. However, their legacy will live forever, and their names and accomplishments are known to mathematicians worldwide. It's therefore very appropriate to have a prize for a young, outstanding mathematician from a developing country named after Ramanujan. So at this point, I think it's appropriate to award the prize.
So let's also hold them to give the prize because the Fernando is
Okay.
So then the last part of the program, we will ask the Ramanujan Prize winner, Fernando Marques, to give the Ramanujan Prize lecture.
Yeah, so before I start, I should say that for me it's a great honor to receive an award that carries the name of brilliant Ramanujan and also the names of such prestigious institutions. So I'd like to thank the committee, the award, the IMU, also ICTP for the prize. I say that this is a great incentive to me, and I hope that also to others, especially in developing countries, to try to keep doing mathematics. Thank you all for coming here too. Okay, so today I'm going to say a few words about my most recent work, joined with Professor Andre Neves, in which we solved the Wilmer conjecture using the theory of minimal surfaces. So the Wilmer conjecture is a question about surface